Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Our next speaker is Prateek Jain. Prateek did his PhD from UT Austin and is now part of MSR India, and as you also know, he's one of the core program committee members who's part of this summer school. So without much further ado, Prateek.
Thanks, Satish. All right. First, I'd like to give you a warm welcome and also many thanks for staying throughout the day and asking many good questions. And I hope you continue your questions in this session also. So in this talk, I will discuss some of the recent work that has been going on in the world of non-convex optimization for machine learning. So throughout the day, Shizen gave us a very good overview of how optimization comes into picture in machine learning and how many times you can formulate the problem as convex optimization problem and solve them very efficiently at a very good scale. And what has been happening in machine learning community for 15-20 years has been the same philosophy, that you take a problem and you try to cast it as a convex optimization problem for which you know how to give a very solid and fast algorithms. So here we are taking a slightly different view. So there are many problems, especially in the domain of high dimensional statistics, where you end up with non-convex problems. And one obvious approach is to use convex relaxation. But of late, there has been another approach, which is to don't relax at all or don't do any relaxation. Just use non-convex optimization as it is. And there are some nice generic tools for non-convex optimization that can be applied to several of these problems. And one can solve these problems efficiently and with theoretical guarantees. Okay. So in this talk, I will try to just give you a very high-level view of this recent line of work. So first I will start with a problem which sort of highlights why estimating a large number of parameters is important for several machine learning problems, and how do you handle those problems or handle those issues. So this first problem comes from the domain of text processing. So suppose I have a Wikipedia document and I want to classify or I want to figure out what all labels are present in this Wikipedia document. So typically the way you represent your document is using a bag of words. That is, you think that document is just a bag of words. I will just count how many times each word occurs, and I will just form a vector out of that. So if my dictionary has, let's say 100,000 words in it, then I will form a 100,000 dimensional feature vector where ith coordinate corresponds to that ith dictionary word, how many times what is the count of ith dictionary word. Okay, so this will give you a vector like this, and you can easily see that if typically your dictionary will be very high dimensional, like it will have 100,000 or more words. So the number of your dimensionality is going to be very large, but many times that is not enough. The simple bag of words model is not enough. You might want to use more fine-grained or more interesting features here. For example, let's say you will count co-occurrence frequencies. So you will look at the bigrams and you will see that how many times words like the machine comes together or machine learning comes together and form a feature out of that. So if your original dictionary had 100,000 features or 100,000 words, then you can see that now with bigram you have increased your feature dimensionality even more, like it's almost square of 100,000. Okay, so that says that the the documents or the features that you have to handle is really large. And even if you want to learn a simple linear model, that means that you have to learn a d-dimensional vector, right? So your model is the following, that you have these feature vectors which are denoted by x1 to xd, and you want to learn these parameters w1 to wd, so that now your function will be either an inner product of w with x or some sort of link function on top of this inner product of w and x. And that means that the number of parameters that you are learning is huge. So that poses several critical problems. So first problem is that the number of training documents that you will need will be very large, because typically statistics tells us that without any other assumption, we need around order D samples or order D training examples for you to be able to learn these D parameters. Okay. So the number of training documents that you will need will be really large, and that's very hard to obtain. On top of that, your prediction and storage will also become very large, because you have to store all these D parameters, and then at test time you have to use all these D parameters to figure out the final prediction value. Okay. So this becomes a huge problem, and we need to avoid this, and a simple way to avoid this is that we'll say that not all D-dimensional vectors are interesting to us. We will try to restrict ourselves to a small set of model vectors. I will not consider every model vector in the world. Okay. So we'll discuss how you can put that restriction. Okay. So let me give you one more example. This example comes from the world of recommendation system. So let's say I have a bunch of users and bunch of movies, and some of the users have rated some of the movies. So all these blocks in yellow denotes that this particular user, so let's say user number 6 has rated movie number 1, and the rating that he has given is 5. Okay. So several new modern systems have this information. So Flipkart will have this type of matrix for its users versus items. Netflix has this information. Amazon has this information, right? And now all these companies, what they want to do is they want to fill in this matrix so that they can figure out for a given user what are the most interesting products or what are the most interesting movies. Okay. So again, if I treat this problem as a parameter estimation problem, where every unknown entry in this matrix is a parameter, then I have to estimate many parameters here. Like if I have, let's say, just 1 million users and 10,000 movies, that means around I have to estimate 10 billion parameters. And again, storage, prediction time, all those will be painful. Well, they will be very expensive. On top of that, I cannot even learn these parameters properly, because the number of observations that I have is very small. Okay. So again, we need to impose certain problem structure here. Okay. So as I mentioned, that whenever you are dealing with a large number of parameters, you need a lot of training samples. Your training time goes up obviously, and on top of that, your storage and prediction time is also very large. So what you need to do is impose some structure which makes sense for the problem. Okay. So for example, for the problem of document classification regression, what we can say is that not all features are important. So many features, like let's say I have just words like they are not important. I don't really need to learn a model vector which puts some weightage there. Okay. So I will try to learn a model vector which puts weights on very few words. That is, the model vector is very sparse. It has very small number of non-zeros. Okay. So for example, let's say even though I want to learn, say, 1 million numbers or 1 million parameters, I will try to learn a model vector which has only 100 non-zeros. Okay. And this immediately means that the number of parameters that I need to find out is just S log D, 100 log 1 million, which is like 600. Okay, that's a good question. So we need to estimate S parameters, right? But I don't know the location of those S parameters. So for every non-zero, I can figure out where it is non-zero by using log D bits, because I have D-dimensional vector. So for every parameter, I have log D bits required. So I have S log D parameters. Okay. Any other questions? Yeah.
This also assumes that the indices of S are fixed. What if we have to get different subsets?
Yeah, this will allow all the subsets, right? I'm just saying that there are S non-zeros. There are 100 non-zeros. Those 100 non-zeros can be anywhere. In your 1 million dimensional feature vector, they can be situated anywhere. And that's why that extra log D factor is. Because that will be used to specify where the non-zero is. Okay. Great. So as soon as I restrict myself to just these many parameters, so first of all, my storage goes down. My test time will also be very small. Now I can just test with using these many flops, right? On top of that, my training cost or number of samples that I need should also go down, because the statistics is telling me that if I need to estimate S log D parameters, I should have around these many observations. So getting 600 documents classified or labeled, that's not very expensive. You can do that, right? So that's also very small now. Okay, but this will pose another problem, which is how do you find these parameters? So earlier we were able to pose these problems as convex optimization problem and solve them, but now I am trying to find a problem where I am restricting myself to all the vectors which have only S non-zeros. So that has an additional problem structure, and my optimization becomes significantly more challenging. So that's what we will come to in a couple of slides. Let me also go back to the recommendation system. Yeah, sorry. This is just a vector. So this vector we are restricted. No. So matrix is data matrix. That is certainly very sparse. But now, right now we are talking about the parameter vector. So remember, our function fx is given by inner product of w and x for any data point x. So what we are saying is that this vector w is sparse. X is certainly sparse, but that does not mean that w will be sparse. We are imposing that extra structure that w will only care for sparse w's, because our budget is not allowing that, number one. And furthermore, in practice, people have seen that that turns out to be much better actually. Yeah.
So you told that you were going to reduce this only S number of parameters, yeah, because you want to like remove all the A's and the, but those are your stop words, right?
Yeah.
They will have a very, you will have, okay, out of 1 million, 1,000, maybe 2,000 stop words, but the rest of the stuff is still there, right?
Yeah.
So why are you reducing all of the stuff to 100?
So the main point is that, let's say if I have just 5 type of topics or 5 classes, let's say sports and science and politics, things like that, maybe there are only small number of words that combine to give you the class. Not all words are important.
In that case, if the dictionary size itself is reduced largely, then why don't you work with a smaller feature space to start with?
That's a very good question, but I will not know that in a priori. So this is also doing this feature selection, or it is helping me trim down dictionary size also.
No, to take synonyms and to club them together.
Yeah, but that still might, 100 million to you, maybe you will come down to say 50 million, but I don't know how to decrease it even more. Like a priori, you don't know what all features will be important. So in here, in fact, features are very transparent. Here I am saying that they are words, but there are many situations where features are not that transparent. Like what people do is, like I have some base features, 100 base features, then I know that there is not a linear classifier in this base 100 features. So what I will do is I will just add some junk features. So let's say I will take x1, x2, I will take x1, x3, I will take x1, x2, x3. So you do all those things, you have some domain experts, they will also tell you lots of features. But a priori you do not know which feature is important. You just add all those features and hope that your learning algorithm will itself tell you that this feature is important. And that hope has one big issue, that if you do not have enough documents or if you do not have enough training points, then your learning algorithm can easily overfit, even with a lot of regularizer. And that's where this thing comes in picture, that what you are saying is that my belief is that world is very simple. There are only just 100 features which are going to be important, and the rest of the features are just spurious. I can just easily ignore them.
Find out which are the features you would ignore.
So this is helping you. Yeah, so this will precisely do that. So this is the other problem, the recommendation system problem. So here, as I said, that rating matrix has a lot of parameters, but here again you can sort of say that suppose I'm imposing this structure that rating matrix is nearly low rank. What that means is that I should be able to write this rating matrix as product of two very skinny matrices. Two matrices U and V, which has just R columns, where R is much smaller than the data dimensionality. Okay. As soon as you do that, again the number of variables reduced to D1 plus D2 times R, rather than D1 times D2. Now assuming R is much small, like R is let's say 100, this sort of reduces the number of parameters by quite a bit. And again, in this problem domain, this assumption makes sense, because what this assumption is sort of saying is that there are just very few hidden or latent factors which dominate how a user rates a movie. So for example, typically the way a user rates a movie depends on very like small number of latent factors like demographics of the user or actor in the movie or genre of the movie. So this is precisely capturing that intuition. Okay. Any questions about this structure? Not necessarily, because accuracy was not there earlier at all. Because if you want to learn all these parameters, you need many observations, which means that I have to get entire matrix filled. So, so this is just sort of reformulating the problem so that problem makes sense. But yeah, if you restrict yourself to very small rank, then obviously slowly you will lose on accuracy. You might be better, but there will come a point where beyond which you will start doing worse because you do not have that many observations. So there is this computational trade-off. For the but I don't. So this R I'll sort of tend to fix arbitrarily. Like I'll say 100 or 200. I don't know. So here in this example, I don't know demographic of the user or genre of the movie. I just have this matrix. Okay. So those are latent factors. I'm postulating that maybe because those are these small number of factors that govern the ratings, and that's why this matrix will look nearly low rank. Yeah. So as I said that you can think of every row in this U as a feature for the user. Okay, so you are automatically learning features for the user. Nobody told you the features, but just by looking at his rating pattern, you will try to figure out what sort of user he is, and similarly for a movie. So for example, let's say, I'm sorry. Yeah, so every row is a movie and every column is a user. So I mean, basically, let's say if there are some 50 users who are essentially college students, so they will like a particular type of movie, and just by looking at their rating, you will be sort of able to estimate that all these users are very similar to each other, and they have these latent factors or these features. So you are automatically learning those features from the ratings matrix. No, you don't. You learn them. So you just know these ratings, and from that you learn these latent factors. You are just given this, and the goal will be to decompose this matrix in this form. Any other questions? Okay, great. Yeah, so R typically has to be like it's a parameter. So you have to do some sort of cross validation, or if you're a domain expert, you have some idea about it. Okay. All right, let's move. So as I said that in both these problems, and there are several other problems where you can impose a structure on the parameters that you are learning. And that makes problem tractable in a statistical sense, that in the sense that you decrease your number of parameters, and that's why the number of observations that you have are enough to estimate those parameters properly. Okay. So the type of optimization problem that it will lead to is the following, that let's say I'm trying to figure out this parameter W, then I'll try to solve this optimization problem where this L of W is a fidelity term. It is sort of a loss term. So remember in morning, she then showed us different type of losses like square loss or hinge loss or logistic loss. So you can use whatever favorite loss function that you have. But on top of that, what we want to say is that W is not any arbitrary vector. Now W satisfies certain structural constraints. So W belongs to certain set C, where C denotes the structural constraints. Okay. So for example, in the document classification regression problem, C is the set of all sparse vectors. So here this notation, what it says is that L0 norm of W is essentially the number of non-zeros in W. So this is just a simple notation there. And similarly in the matrix completion or recommendation system problem, Set C is set of all matrices whose rank is bounded by R. Okay. And now you have to solve this problem for certain loss functions. And that's where the main challenge comes in, because the thing is, by imposing the structural assumption, you made life very easy in terms of statistical efficiency. But finding these W parameters become much more hard. In fact, in general, they become NP hard. So for example, for the sparse regression case, the optimization problem that you have, even for very nice loss functions like a squared loss function, the problem in general is NP hard. And the main hardness comes because this set of sparse vectors is non-convex. Okay. So I'll explain where that comes from. Well, actually, I have a slide to show. I'll come back to it, sorry, to find the slide. But trust me that this is a non-convex set. And similarly, in the rank minimization case also, or this when the constraint set is set of all low rank matrices, then also problem is known to be NP hard. In fact, in this case, it's known that problem is even NP hard to approximate within certain logarithmic factors. And the main challenge again comes because non-convexity of rank. Okay. So here, as I said earlier, that one sort of very popular approach is to just relax the non-convex part of the problem to convex. So here, remember, the main challenge is coming because of the constraint. So what we'll do is we'll do a convex relaxation of the constraint. So for this L0 ball, or this set of all sparse vectors, the best known convex relaxation method or convex set is known to be L1 norm of the vector W. So L1 norm is defined by summation I Wi. This should be equal. Summation over I mod of Wi, sorry. So this is a convex set, and now what you will do is you will just work with this relaxed set. So you can include several vectors which are not sparse. Your final solution can be something which need not be sparse, but it will have a guarantee that L1 norm will be small. Okay. Similarly, for matrix completion, you can relax your set to be something called to another set where trace norm or nuclear norm of the matrix is bounded by something else like lambda r, where nuclear norm of the matrix is given by some of its singular values. So I won't discuss this much today, but this sort of stuff will be discussed by Praneeth in next week's talk. So, but the main point is that there exists some very nice convex relaxation based techniques which you can apply to these problems, where basically you can take your non-convex set and relax it. Okay. And that then brings in all the nice things about convex optimization, because it's a convex optimization, we can solve it under tool sets in polynomial time, and there are some very generic analysis methods available to analyze how good your final solution is. Okay. But the main problem is that rather than optimizing over a much smaller set, now you are optimizing over a much bigger set. Okay. And that slows down your optimization quite a bit. And like if you look at these optimization sets, this L1 norm of a vector is not a differentiable function. So it's a non-smooth optimization. So although it's convex, but because of its non-smoothness, this also tends to be very, very slow. Okay. And it does not scale very well to large scale problems. Okay. On the other hand, other approach is a direct approach, which is don't relax at all. Just use certain simple existing techniques for optimization for these problems. So for example, there is a very generic approach called projected gradient descent. You just directly use that to your problem, and then hope would be to show that for the particular problem that you are considering, assuming certain model, you will be able to show that this method is not arbitrary. It converges to the global optima and is doing something very reasonable. Okay. So that's another approach. Okay. So let me briefly discuss this projected gradient descent method. So the idea of this method is very simple. So let's say this is my function. I am at some point, let's say W0. What I'll do is I'll look at the gradient, and just move in the direction of negative gradient, which I know will definitely decrease my objective function value. Okay, but while doing this, so this step is mimicked by this equation. So I will take Wt, I'll walk in the negative direction of the gradient of the loss function. Okay, but while doing this, I might go out of my constraint set. Remember, I wanted to constrain myself to set of, let's say, only sparse vectors. So this step will take me out of that set. Okay, so what you can do is you can project back onto that set. So let's say, yeah, sure. So remember, I mean, when you take a gradient step, it need not, so you wanted to lie in a small non-convex set. So let me use the, where is my, oh, sorry, okay, yeah. So let's say this is the set of parameters that I'm interested in, and let's say I was around the boundary, this was my Wt. Because of the gradient step, I moved in this direction. This was my direction of maximum gradient. Then I will move in negative direction of this. I will come to this, and this is outside the set. So now what I'll do is I will project back onto this set. Okay, so that I am in that set, in the set of sparse vectors, let's say. Yeah, so I'll do it in a couple of slides, but PC of Wt plus 1 is argmin of W minus Wt plus 1 square. Let's say we are doing projection with respect to Euclidean now, such that W belongs to the set C. Yeah, here we are using L2 norm projection. So OMP is a particular type of this algorithm. It's a very specialized version of this. OMP is orthogonal matching pursuit. It's a greedy method, but it can be cast in this framework. BMP is basis matching pursuit. So that's L1 regularized algorithm. And as I said, that they do not scale very well. So we'll show some experiments results, which also seems to denote that, seems to show the same thing. Any other questions? Yeah.
This is for the non-convex problem or the convex?
For the non-convex. For convex problem also you typically use projected gradient descent, but for non-convex also we can try to use it.
Won't it get stuck to a local?
It can get stuck in local minima. That's what we'll show, that under certain model assumptions, which anyways are required by the convex relaxation based methods, under those same assumptions, we'll show that this method converges to the global optima. Yeah, we are assuming that L of W is very simple. Say L of W is just a simple least squares problem. So I'll give the precise form of this. But you can think of LW to be the nicest favorite function that you want to think of. Square laws, logistic laws, whatever. Okay. All right. So note that this projection that you need to do in the end is projection onto set of to a non-convex set. And again, that is also known to be NP hard in general. So I sort of just bluffed around. I just reduced the problem to another problem which is also NP hard. Right. But here the nice thing is that for several of these structural assumptions that we have, projection onto these non-convex sets is also possible in small amount of time. So for example, for the set of sparse, like sparse linear regression, or when the set of vectors that I worry about is the set of sparse vectors, there the projection can be done in time d log d only. And similarly, for the low-rank matrix world, the projection can be done using singular value decomposition. So again, I won't talk much about it, but Praneeth will talk about it in a lot more detail. Okay. And the interesting thing is that by using this simple sort of trick, that is just using projected gradient descent or some small reformulation of the problem, you can show that the simple non-convex techniques also converge to the global optima for several problems. So now we have, like, big list of problems where these type of things work. I won't go in any of these things. In this talk, I will just talk about the first thing, and in tomorrow's talk, I will try to cover one of these two topics. Okay. All right, so let's come to the problem that we will be focusing on for the remaining talk, which is the problem of sparse linear regression. So problem, as I defined earlier, I have some data points. I want to learn a parameter w, so that x times w matches y as closely as possible according to some laws, and we want that w is as sparse, and we know, and we are in a setting where the number of observations that we have is much smaller than the dimensionality of the problem, or the number of parameters that we want to learn. So let me give you a couple of quick motivating examples for this sparse linear regression. So already text processing world and computer vision, most of these problems anyways face very high dimensional data and needs to do regression there. So they are candidate applications, but there are several other very sort of interesting applications for this work. So sparse linear regression is another name for a popular field called compressive sensing. So in compressive sensing, what you want to do is, let's say you have some signal like image, you want to record this image or measure this image using as small number of measurements as possible. So let's say if I want to figure out, or I have a scene, I want to capture it, and I want to capture it at a resolution of 1 megapixel. Then typically, like, if I don't do any compression, then I will need 1 million measurements, which means that I need to put 1 million sensors on my small camera. That's not going to happen. Right? So I want to say that by using very small number of measurements and very small number of sensors, you will be able to capture these images at very high resolution. Okay, and there we are using this notion of sparsity in images very critically. We want to assume that this signal or this W parameter is very sparse. But if you think about it, like real world images are not very sparse, right? I mean, they will have this lots of colors, and then they are, at least they are, if nothing else, like if you are just capturing gray, then also half of the pixels will be black or white or gray, right? So you are not going to get a lot of sparsity here, okay? But images are very sparse in a particular basis called Haar wavelet basis. And there the main intuition is that the number of edges in an image, in a natural image, is going to be very small. Images are not, like natural images are not just random white noise. They have a lot of structure, which means that there are very few edges in the image. There is a lot of continuity in the image, okay? Which means that if you look at something called Haar basis of this image, or Haar wavelet coefficients of this image, they are going to be very small. So for example, for this 1 megapixel image, the number of Haar wavelet coefficients which are non-zero are like barely 100 or so. So image, although in pixel format, is not sparse, but if you look at an appropriate basis, it is very sparse. And what we will try to do is, we will try to reconstruct this image in this sparse wavelet basis. Okay. So that's one application of sparse linear regression. Another come from the domain of computer vision. So let's say I have an image that can have several labels, and I want to figure out all the labels or several objects, and I want to figure out all the objects. So I want to figure out that this image has flower and dog and cat. So again, the number of possible categories that are there in the world can be very large. So for example, in this very sort of academic data set called ImageNet, that itself has around 20,000 categories. Okay, so the number of categories is very large. So if you think about the label vector, your label vector is very large. Okay, but if you look at a real world image, that is going to have just 5 or 10 objects. So again, the label vector of an image is going to be very sparse. Again, sparsity comes in picture. Okay, and now your goal will be to figure out this sparse label vector using certain properties of your original feature space. So I won't go in much detail there, but the main point to note here is that again the parameter vector that you are trying to estimate is very sparse, and that's why the sparse linear regression things are very useful. So it can be used to model several applications. Okay. So let me just skip this. So this is the final optimization problem that we are trying to solve, at least for the purpose of this talk, that we want to find out a w so that y minus xw square is minimized. So I am fixed my loss function to be least squares here. You can use any other loss function, but for now we'll just stick with the least squares. And we want w to be as sparse. Okay. And as I mentioned earlier that this problem is NP hard because of non-convexity of this L0 norm. So let's just quickly look at why this set of sparse vectors is non-convex. So you can see that this vector, which is one sparse, and similarly this vector is also one sparse. But if you take an average of them, then you get this vector which is two sparse, or which is two non-zero. So you have gone out of the set. So you are taking average of two vectors which belong in the set of one sparse vectors, but just by taking an average you have gone out of the set. So it's a non-convex set. And as I mentioned that here a typical approach is to use convex relaxation. That is, you relax this L0 ball with L1 ball, and if you take your objective constraint in optimization problem, then it reduces to what's called lasso problem, which is very, very popular for this sparse linear regression. There is like every year there are like at least 40-50 papers written on how to optimize this problem for very large scale data sets. And the main challenge in optimization this problem comes because this L1 norm is non-differentiable. And as Chizen talked about a little bit, that if you have non-differentiability, you do not know which direction to go in. There are several possible directions in which you can go in at a given point. And that's why it's very hard to optimize for very large scale data sets. Okay. On the other hand, we were just interested in this projected gradient descent approach, right? So where we'll do a gradient descent, project onto this set of sparse vectors, and this projection can be done using a very simple trick. So what you will do is you will take your vector z that you want to project and just sort it, okay, and take its top s elements in magnitude, and that will define your sparse vector, like support of the sparse vector. Okay. So outside this set everything to be 0. Yeah. So z is the vector that I want to project onto this set of sparse vectors. So in the notation that we were talking about earlier, let's say I want to find out, I have done wt plus 1, which is the gradient of, like wt plus 1 I obtained by doing simple gradient descent. Then I want to solve this problem, right? So z here I am just denoting by wt, or wt plus 1 is denoted by z. So what you will do is just take this vector wt plus 1, sort its elements according to the magnitude, and take top s elements. Yeah. Yeah, in decreasing direction, and then just use this top. Okay. And then on the support set, what you will do is you will set your x to be exactly z. So you will just, like if you want to find a w, then on the support set you set it to be exactly whatever wt plus 1 was, and on the remaining just set it to be 0 because I want to be a sparse. You can select any. It won't, like, so you will have multiple optimal solutions in that case, and you can select any of them. So one question is, why is this optimal? Why is this correct? So I will actually leave that as a homework problem. So show optimality of this procedure as homework problem. And in fact, you can show something stronger here. So if, let's say, you are, so this projection always tells you what? This projection tells you that whatever x that you have figured out will be less than equal to all other x's which are as sparse, right? This distance is, this is just by definition of projection, right? but you can show something stronger. That is, if you are comparing yourself to something which is just S star sparse, where S star is much smaller than S, then you get this extra decrease in error. But again, this is a homework problem. I won't go in this talk. Okay. Right. So as I mentioned, that this projection operator tells you this sort of 0th order condition. That is, if you find out some other y in the set, then distance of y to z will always be larger than your distance of projection to z. So PR of z denotes the projection. So projection distance of projection to z is always smaller than all other guys in the set. So that's like, by definition. Okay. And for non-convex sets, unfortunately, this is the only thing that we have available. Whereas in convex optimization world or convex sets, you have a stronger condition, which is a sort of first order condition, which like intuitively what it means is the following, that if let's say this is your set, this is the convex set, this is my z vector, and I project it onto this set, and this is, let's say, my projection, right? Now for any other vector in the set, first of all, this angle is always going to be obtuse. Okay. On top of that, if I look at this length, if I look at my projection of this vector, so this is some other vector y, if I look at projection of y minus z onto this line which join pz and z, this length is always going to be larger than the distance between pz and z. So that's a extra information that you have. Unfortunately, this doesn't hold for non-convex sets, right? So non-convex sets can look something like this. Okay. And that means that if I have a vector, so let's say this is the projection, but this angle need not be, and this is some other vector y, this is z, this is p of z. This angle can still be acute. So this extra information is very critically used by methods which show that for convex optimization, or like when you're projecting onto convex sets, then projected gradient descent works optimally. We cannot use that intuition here, the non-convex case. Okay. And that's why, in fact, like the problem in general is known to be NP-hard. Okay. But by imposing certain restriction on the data matrix, we can make the problem tractable. Okay. And one of the most well-known or popular restriction that's known is called restricted isometry property. So restricted isometry property, what it sort of says is that for all sparse vectors W, this matrix X, which is essentially linear transformation, does not scale the vector too much, it just rotates it. So matrix X, when applied to a vector W, it only rotates it. It won't happen that my W vector, although length of W vector is 1, but length of X times W is almost 0. Or length of X times W is very large, like infinity. Those type of things cannot happen. That's what this restricted isometry property says. So the way to read this property is that for all sparse vectors up to plus minus delta factor, the lengths remain the same. Length of xw is same as length of w. Any questions on restricted isometry property? Not directly, but you need to do some things. Johnson-Lindestros. So first of all, I have not even defined what x is. So, but let's say if we jump forward, x is random. Johnson-Lindestros holds for a fixed set of vectors. So if I have, let's say, n vectors, then Johnson-Lindestros said that I can project onto log n dimensions. But here I am considering all as sparse vectors. So I can have infinite many vectors. So, but idea will be very similar. Shall we move on? So the guarantee is the following, that let's say my function looks like something like x of w minus w star. I want to recover w star, so that w star is my correct parameter set or correct parameter vector that I want to recover. So I will be optimizing this function under the sparsity constraints. And furthermore, as long as my delta 3s, so this RIP constant when read for 3s sparse vectors. So as long as delta 3s is less than half, then this projected gradient descent method converges at a geometric rate. So what this sort of says is that distance of wt plus 1 to w star is at most distance to wt minus w star times this factor 2 times delta 3s. So if 2 times delta 3s is strictly less than 1, then at each step I am decreasing the distance to the optima. So let's say if 2 times delta 3s is equal to half, then that says that at each step I am halving the distance to the optima. So after around log 1 or epsilon steps, I will be within epsilon distance to the optima, to w star. Any questions about the results? And the interesting thing is that at least under this particular set of conditions, the proof of this result is extremely simple. Like it can be done in 5 minutes. I'll try to do that. On top of that, it's a very generic result. So you need not restrict yourself like set of C to be set of sparse vectors. It can hold for any non-convex set as long as your RIP is satisfied and you can do projection onto that set. So you just need 2 conditions. Okay. So it's a very generic technique. Okay. So let me just show you the proof. It's like if I'm rushing through, don't mind. I just want to give you a flavor that why this sort of things work. So we know that we are projecting wt minus the gradient onto set of sparse vectors, and that's why, and wt plus 1 is the optimal solution after that, right? So this is always going to be lesser than equal to w star minus wt plus gt. Okay. So this is just by 0th order optimality condition, right? Nothing special here. Now, the thing is, like one thing to note here is that, so if this is like if GT is a d-dimensional vector, then all the components of GT which are outside the set I, so the set I is a support of WT plus 1 union support of WT union support of W star. So note that W star, WT and WT plus 1, all of them are contained in set I. So whatever elements which are outside this set I, they will cancel from both the sides, right? Like, because you can look at a square also. So this thing can be written as, so if this is a vector, let's say V, and this is a vector U, then this can be written as V restricted to I square plus V restricted to I bar square, and this is U restricted to I square plus U restricted to I bar square. Okay. And V restricted to I bar is same as U restricted to I bar because that is just GT. That will not have any component from WT plus 1, WT or W star. Okay. So we can ignore them, and from now on just assume that all these things are over this set I only. Okay. And the thing to note is that size of I is going to be less than 3 times S, because WT plus 1 will have at most S elements. We did that projection. WT again by induction we know that has at most S non-zeros, and W star has at most S non-zeros by assumption. Okay. So size of I is just 3 times S. Okay. So this means that, so here what I will do is, I will subtract W star and add W star and just apply triangle inequality, which will mean that WT plus 1 minus W star is less than equal to 2 times WT minus W star, no sorry, W star minus WT minus WT minus GT. Remember all of this is over this set I only now. Okay. whose size is less than 3 by 3s. Okay. And if you look at this quantity, this is just also remember that GT, which is the gradient, can be written as X transpose X WT minus W star. Okay. So this is essentially just I minus X transpose X to now, and using RIP remember said that X times W square for all 3s sparse vectors is less than 1 plus delta 3s W square, which essentially means that largest eigenvector, largest eigenvalue of this is less than equal to delta 1 plus delta 3s, and minimum is greater than 1 minus delta 3s. And that's why this thing is simply like just by applying. So again, this step I will be a bit fuzzy, but using simple linear algebra, you can say that this is less than equal to this. So that's it. And here again, as we said, that because 2 delta 3s is less than 1, you will have a decrease to the distance, decrease in the distance to the optima. So here again in the proof, what all we use? So here we just use that the projection is optimal. So you should be able to do the projection, and then this step can be done for all the sets. Here we are doing it just for the sparse case, but it can be handled. And then here we used RIP. That's it. There is nothing else going on in the proof. All right. So let me move on. So so the algorithm that I told you, projected gradient descent, that can have several variations also, and several of those variations then lead to several other algorithms like orthogonal matching pursuit, or there are several other algorithms like COSAMP, SP, whatever. Like there are like 50 other methods. All of them use some or other techniques like this. So one of the most sort of well-known or popular approach here is to use fully corrective version, where first you do gradient descent, find out a support set of the next iterate using your projection operator, and then what you do is you do minimization over that support set completely. Like once I have restricted myself to S non-zeros, and I know that these are the S non-zeros that I really care for, I will do an optimization over those S non-zeros exactly, like rather than just doing a gradient descent there, which is what earlier thing was doing, and that turns out to be much more efficient. Okay. And similarly, you can have several other variants like two-stage algorithms, where first what you will do is, like rather than restricting yourself to S elements at each step, first you will have a phase where you will add many more elements than S, and then you will cut them back. So several of those algorithms are also existing, and all those algorithms can be analyzed under this RIP type of setting using similar techniques. So now one question here is that I am talking about this restricted isometric property, like is this property even satisfiable? Like are there matrices that really satisfies it, and are those matrices really interesting? Like what if the matrices that satisfy this restricted isometric property has n rows and has d rows. So let's say if the matrix looks like this, if I had d columns and d rows, then I am not gaining anything. That says that I need d observations, and that I could have anyways solved using simple least squares. Why do I need all this structural assumption and all? So I would need that this matrix X should be very like it should have very small number of rows. It should be very fat. Okay, and that happens if, let's say X is a random matrix. Each entry of X is 0 mean sub Gaussian or Gaussian distribution. Under that assumption, if you have around S log D elements or S log D rows in the matrix, then it satisfies restricted isometric property. And for Gaussian ensemble, we can make it more precise. So let's say if each entry of your matrix is sampled from a Gaussian, independent Gaussian, and you have around S log D by delta S square non-zeros, then your RIP is satisfied with constant delta S. Okay. Again, the high level thing is that if your data is random, if your data comes from certain sub-Gaussian distributions, and if each row of data is sampled from some fixed distribution, then RIP is satisfied. Okay. And typically those type of assumptions are anyways used to analyze your regression problems, or machine learning starts with those sort of assumptions that every data point is sampled from a fixed distribution. So it's not a yeah, every data point is supposed to be independent in most of the machine learning analysis.
That's your data matrix, right?
Yeah.
Independence seems like a sort of an overkill, right? Because you mentioned things like image and stuff like that.
No, image is a signal. Image is not your data matrix. Data matrix in the image case is something that you generate.
Sequence of images or something like that.
No. So all those are parameters.
Okay.
Image is your parameter, hidden parameter that you are trying to estimate, right? So that's not an issue. We are not making any assumption on the parameter other than sparsity. We are allowing all the parameters in the world which are sparse. The matrix, the data matrix that you have in the image case or compressive sensing is actually generated by you. So you can set it to be IID Gaussian, right? But here I am hiding one thing that I'll actually talk about in just remaining 1 minute I have. That what I'm hiding is that in each row, so each row should be independent, which is fine. Like every data point is independent, that's a standard machine learning assumption. But here I am assuming that all the features are also independent of each other. So if the features have any dependence, then RIP might not be satisfied, and in fact that's what will happen. So if your matrix is like this, or if your data is like this, where ith data point is sampled from a Gaussian whose covariance look like this, where your first and second coordinate has correlation of 1 minus epsilon, okay? Then even if you take infinite many samples, you are not going to satisfy your RIP. Okay? And that's very bad, because I know that as soon as I have samples which is of the order D, my simple least square should start to work. So if this result does not even hold even with infinite many samples, then that's bad, right? But there is a good news that this need not be the case. So if you, let's say, assume a simple like data model where xi is sampled from any arbitrary sigma, okay, and you have some noise also, then you can show that using this hard thresholding type of techniques or this projected gradient descent type of techniques, you will find out your W star up to this error, okay? And here again this error, like things to note in the error is that S log D and N. So you want N to be around S log D, which is good. But there is an extra factor which is kappa, which is the condition number of the matrix. So that comes in picture. Kappa is the condition number of the covariance matrix. It's the largest eigenvalue of the covariance matrix divided by the smallest eigenvalue of the covariance matrix. So the earlier example that I gave, like if sigma is around 1 minus epsilon, 1 minus epsilon, here the condition number will be something like 1 by epsilon. So it's going to be very large. But this is what it is, like you will have that factor there, okay? And interesting thing is that you cannot even avoid this factor. So in a recent work by Michael Jordan, Martin Wainwright and their student, they showed that if you want a efficient algorithm, then you will have a factor like this in your error bounds.
So you want the data to be strongly correlated, that's what it's trying to say, right?
No, you don't want.
No, I mean, if it's weakly correlated, the condition number will be very large.
No, condition number becomes very small when they are weakly correlated. If they are independent, the condition number is 1. If they are more and more correlated, so for example in like the example that I gave, so in this sigma, coordinate number 1 and coordinate number 2 has correlation of 1 minus epsilon, where epsilon is like say 0.0001. Okay, they are almost the same. There is just small difference between them, and in that case your condition number becomes 1 by epsilon. It's very large. On the other hand, if the two variables or two features were independent of each other, then your correlation matrix will be 1 1 0 0. and in that case, both your eigenvalues are 1, you are good to go. Yeah.
So if there is correlation, if you do a PCA and transform to a space where they are uncorrelated,
That's a very good point, but the problem, remember, is that we have very few observations. So your dimensionality is D, and you have very few observations. So to do that PCA thing and doing decorrelation, you will need again order D samples. So you cannot apply that thing. In fact, PCA is much harder problem in some sense than linear regression. Yeah, here, I mean, in this sigma I assume, but it need not be. I mean, so, I mean, if you do not normalize your features, then what will happen is that you will have one more term here, like this, rather than just being sigma 1, lambda 1 sigma times lambda d sigma, you will have a extra lambda 1 sigma setting. That's all. But that is just a normalization thing. This is something that you cannot get rid of normalization. That's not a just scale issue. It's a so this is, and this is a, like, according to me, it's a like a phenomenal result, because it sort of says that like not well. So what this sort of says is that there is a big gap between your computational efficiency and statistical efficiency. So statistically, just S log D samples were enough, but to get a computationally feasible solution, you need this kappa times S log D, or kappa square times S log D samples. So there is a gap between your statistical efficiency versus computational efficiency. Obviously, all of this is assuming P not equal to NP. Yeah.
can I ask what is the reduction, the hardness reduction?
So this reduce it to SAT. Yeah, but yeah, but I don't understand that reduction quite a bit. It's a very nice and challenging result, I think. So yeah, I'll skip this part. This just minor thing here, that here I was just talking about least squares problem, but you can have any other function f, any arbitrary function f. Okay, and also this function need not be 0 at w star. It can be, it can take any arbitrary value. All right, so so here I just wanted to point out one thing, that if you do simulations and compare also theory versus practice. So in theory, both L1 or this convex relaxation based method and this simple projective gradient method, they have almost same performance or same guarantees. But in practice, things are very different, especially because L1 requires solving this convex optimization problem, and even after a lot of hard work, one typically sees that non-convex methods are much faster than convex methods. So this is the runtime of the algorithms, and this is on x-axis. I'm varying the dimensionality of the problem, and here we can see that as dimensionality is increasing, non-convex methods still have it's like taking like few milliseconds on top, but convex methods, their runtime is increasing heavily with increase in dimensionality. Okay. And similar, like so on several other parameters, both the methods, like in terms of recovery, they have similar thing, but in terms of speed, they are very different. So for example, if you increase your noise level, recovery of this HTTP is a non-convex method, and L1 is the convex method. You can see that they have almost similar type of error. This is the error here. They have similar type of error. So there is no difference in their performance as such, performance in terms of error or in terms of recovery. But in terms of runtime, there is a huge difference. Okay. All right. So in summary, we looked at some of the high dimensional problems, and whenever you have high dimensional problems where you have to estimate large number of parameters, one very sort of intuitive way to approach it is to restrict the set of parameters that you consider. You want to restrict yourself to, say, set of sparse vectors or low rank vectors or some combination of them depending on the problem. Okay, and here in this talk we focus mostly on the set of sparse vectors, And we show that projection onto this set of sparse vector is very easy, and because of which one can define this projected gradient descent very easily, implement them very easily, like it's just a, like, barely 5-line implementation in MATLAB. And as long as certain properties like restricted isometric property or restricted strong convexity are satisfied, which are fairly like generic techniques, like they are indeed satisfied for several real world data sets, your projected gradient descent works. Okay, and there exist several variants. So the simple projected gradient descent might not give you the optimal solution or like best performance, but by doing simple things like fully corrective methods and all, you can improve their performance quite a bit. Okay. And finally, like there are several other structures that can be used to solve this problem. Right. So finally, I'd like to acknowledge my co-authors on some of this work. So Purushottam and Ambuj. Okay. Any questions?
Okay, then we'll end the day today. Thank you, Prateek.
Okay. Thank you.